Okay, so when we're solving problems like this, one of the things I started to realize is that what is really making calculus difficult for us is the pre-calculus. So what I'm going to do here is show you kind of basically how I would approach this problem, and then let you know how we can approach this problem on distance learning. Okay, so first thing I'm going to look at is I've got two sine functions. And granted, there's more going on here, but I've got 2 cosine x times sine plus sine of x equals 0. Well, algebraically, if two factors share something in common, we can pull that factor out. And when I do that, I'm factoring a sine away. And what that allows us to do is use the zero product property where each factor must be equal to 0. And then we have to solve. And if I subtract 1 over here and then divide by 2, I get 2 options. And we've talked about this one quite often, sine of 0. That should be really friendly and quick, but we didn't really do a lot with solving when it's not on one of those quadrantial angles. So I'm going to just solve this really quick. When is sine equal to 0? Well, sine is always the y value. And where is it equal to 0? On the interval from 2 to pi, or excuse me, from 0 to 2 pi. It's equal at 0. And then again, sine is 0 at this point on the unit circle. So at pi, and it's also equal at 2 pi. However, 2 pi, I'm going to put parentheses around that. Mr. Waffler did that in his video, and I kind of liked that because it's not part of the interval, but we're still thinking that it's there. So the possible x values that make sine 0 is when x is 0, when x is pi, and when x is 2 pi, but we're going to put parentheses around that 2 pi because that's not in the interval. All right, so those are my answers for the first part. And I'll just include these because of the open bracket. But what about when we have cosine equaling -1/2? Well, if you've memorized unit circle, you got it and you know this answer and you're done. But if not, then you have to think of, well, what is cosine? Cosine is the adjacent over the hypotenuse. So one of the things I like to do is think of this also on the unit circle, but realizing that if the adjacent is -1, it's going to bring me over to the left side of the graph. And then my hypotenuse is 2, and that forms a special kind of right triangle right here. This has to be a square root 3, and it's a 30, 60, 90 with the 60 degrees coming right across from the square root of 3. So this reference angle is 60 degrees, which is the same as pi over 3. But my answer is not pi over 3 because pi over 3 is in the first quadrant. We would have to take, basically, if I go all the way to 180, that's pi, right? Well, what if I call pi 3 pi over 3, but now I'm 1/3 less than that? That would put me at 2 pi over 3. And there's one of my answers. But this exact same triangle can be drawn right down here because we still would go -1 to the left. Hypotenuse is always positive, and that would just make this a negative squared 3, but we're not dealing with the opposite. We're looking at the adjacent and the hypotenuse. So that's 60 degrees here, which is an extra pi over 3 past 3 pi over 3. So that would give me 4 pi over 3. So that's how I deal with it. I think I've shared with you, I haven't memorized unit circle. But we're in distance learning right now. And if you're taking the AP test, there's a very strong chance that you're going to be taking it from a computer at home, which means you will be able to print off some form of a unit circle and have that at your disposal. I'm going to send a link in the chat right now. I just found this really quick, but if you do a search of unit circle PDF, you can pick whatever version you like best. All right, so let me show you how quick this is. And again, you hopefully are familiar with unit circle, but what do we know? We know that in every ordered pair, we've got the x values are cosine, the y values are sine. So if I want to solve this first one, when is sine equal to 0? Then I'm looking at the y values here. And we drew this really quick, so we know the answers are 0, 2 pi, and pi. So those are the answers to my first part. And then we got, when is cosine of x equal to negative 1/2? So you have to know that, I want to make that blue. You have to know that cosine is the x value. So I'm going to look for the x values, but I want it to be negative 1/2. So when is cosine negative 1/2? At 2 pi over 3, that was my first answer. And then it's reflected, so right here at 4 pi over 3. So that's my advice, is if you have the ability to print this unit circle, print it. If you want to take the time to redraw it and generate it, awesome, do it. What's going to happen is if you take the AP test, they're probably going to have a lockdown browser where you won't be able to access any other sites. So you don't want to rely on the fact that you need to pull this up. So have a hard copy available or some other form of viewing it. All right. Now I mention that because we have our test coming up after today's class. I'm going to open the test up, and you'll be able to take it anytime from now until Sunday night at 9 p.m. So you just have to get it done by then. And I'm going to encourage you to have the unit circle available if you need it. I think, if I remember right, you'll need it for one problem for sure, maybe two. Okay. But as always, ideally, it'd be great if you had it memorized or you knew the other methods for finding. And the other methods are based off of 30, 60, 90, and 45, 45, 90 triangles. And that link that I put in the chat actually has a reference as to how all of these are generated. So you could read further if you want to. All right. So really quick, we got to have a small conversation. All right. So this question here asked us to analyze the graph of f prime. Now, we've done that throughout the year, but we're starting to focus on it a lot more recently. So I'm going to make a stronger connection to this. So we know that this is the graph of the derivative of f. Which of the following statements is true? Well, here's what I would do if I was doing this problem. I'm way more comfortable looking at sign charts. Now notice, this is the graph of f prime. We can quickly make a sign chart of it. Where is f prime equal to 0? Right here at 0, and then again at 2. Right? Those are the spots where we cross the x-axis. Well then, what's happening as I look at the values of f prime to the left of 2? Well, notice, all of these values right here are above the x-axis, which tells me this is the graph of f prime, so those are greater than 0, which means the sign of f prime is positive. And then anything below the graph, below the x-axis, is between 0 and 2, and those are negative. Right? That's when f prime of x is negative. Now, notice, the sign chart tells us the exact same thing as the original graph of the derivative. It's just some students are more familiar with this. So now let's look at our pieces. The f, and notice, all of these questions are related back to the original function f, not the graph of the derivative. So we have to interpret this and make a conclusion about the original graph. So this says f is decreasing. If f is decreasing, that means that the derivative has to be less than 0 on the interval from -1 to 1. Well, notice, here's -1. -1 is positive according to our chart, so it cannot be a. All right, f is increasing from -2 to 0. So since the original function is increasing, that means the derivative has to be greater than 0 on the interval from -2 to 0. And notice, from -2, which I guess I could call this well, I don't want to call this -2 because officially that's not a critical point. But that's where our interval stops. So from -2 to 0, it is positive because we are above the x-axis. So right now, this is the only one that's true, which means I could be done because I know for sure that's true. But let's look at why the other ones are not. This says f is increasing from 1 to 2. If f was increasing, the derivative would have to be greater than 0. Well, from 1 to 2, our derivative is below the x-axis. It is not increasing. F has a local minimum at 0. Well, wait a minute. Here's 0. What's changing? We're changing from a positive slope to a negative slope. So I'm going up to down on the original function, which means there's a maximum at 0, not a minimum. And then f is not differentiable at -1 and 1. Well, notice this is saying the original function is not differentiable. That's not true because the derivative exists, right? That's a filled-in circle. If it was a non-filled-in circle, an open circle, then the derivative wouldn't exist. Remember, this is the graph of the derivative, but they're both filled in. So f is differentiable at those spots. Now, if we were to look at what do these corners mean, because some students are like, well, wait a minute, I thought you said corners meant it's not differentiable. That's true, but if this is the graph of f prime and we're comparing the slopes of this graph, then we would be talking about the second derivative. So the second derivative is undefined at these 2 points because of the corners. All right, so there's the first one. The next one, what I noticed was overall, the calculus seems to be going fairly decent. It's the pre-calculus that's tough, and that's always been the case with calculus. So I don't want you to feel bad about that. That just means we really have to kind of shift our thinking here. So what do we got? We've got f is the function from the interval, and you can always rewrite this interval if you'd like. They're saying we only want the answers between pi and 2 pi. And then it says find the absolute max and the absolute min. So what do we need to do? Absolute max and mins occur at critical points. I need to take the derivative. There's a chain rule here. The derivative of the outside is ln, so that's 1 over x, but I'm not going to write x. I'm going to take whatever was on the inside and keep it there. And then we've got the chain rule, and the chain rule says now multiply by the derivative of the inside, and the derivative of 2 is 0, the derivative of sine is cosine. And I was really encouraged. You got 1 point for getting this far or condensing it to cosine over 2 plus sine. Right? And in my mind, that's the calculus side. All right, so I was encouraged that we got that, but what do we have to do? We have to set the derivative equal to 0. You got 1 point for showing that you set the derivative equal to 0. And then what I noticed is this is where students got stuck. The solving part. Well, here's what we have. We have a fraction equaling a number. Let's make that a fraction. And my guess is if I just showed you that one piece, you would then kind of instinctually say, oh, that's cross multiplying. 1 times cosine is cosine, and 0 times anything is 0. So now I have to figure out when is cosine equal to 0. And you have a couple of options. If you want to, whoops. If you want to just go ahead, and since this is a quick one, I'm going to do it. When is cosine equal to 0? Well, cosine is the x value, so that would be up here at pi over 2, and then it would be down here as well at 3 pi over 2. All right, now we have to be really careful because one of these answers is not in the given interval. I want the answers between pi and 2 pi, which excludes pi over 2. That's not part of our interval, even though that's an answer. So the only answer that I'm looking for is 3 pi over 2. Okay? Now, we're not done, right? This is a critical point. That's where the derivative is equal to 0. So we know there's a horizontal line. I don't know if it's a max, a min, it might even be a flat spot, okay, one of those plateaus. So what we have to do then is anytime you're finding the absolute, all I want to know is which one is the highest output, which one is the lowest. Then you're going to test the critical points. And the endpoints. And we test them in the original function because I want to figure out which one is the max value or min value. So what do we need to do? We need to test the endpoints, right? Pi and 2 pi. And then I need to test the critical points, and there's only one of them because of the interval. Okay. So now we're going to go ahead and test pi into the original function, ln of 2 plus the sine of pi. And then I got to think of, okay, well, what is the sine of pi? I'm thinking, here's pi, and if I went over -1 up 0, sine is the y value, so this is 0, which means my answer is the natural log of 2, because 2 plus 0, natural log, there you go. And you don't have to write a decimal, that's fine, just leave it like that. It's actually preferred that way. And then I have to test 3 pi over 2. So then we're thinking again, ooh, what is the sine of 3 pi over 2? I already have it set up. 3 pi over 2 is right down here, and the sine is the y value. So this is -1, which means I've got the natural log of 2 minus 1, or the natural log of 1, which they are going to assume that you know that that is equal to 0. The natural log of 1 is always 0. All right. And by the way, all this work that I'm doing right here, you don't have to show. If you can do that in your head, do it, because we don't want to waste a bunch of time showing work that they're not even going to look at. Right? Or I should say, if you make an error here, I'd rather just have you get the right answer. And if you can do this in your head, do it. What would you do? You could say, well, what is the sine of pi over 2? Okay. Well, sine of pi over 2 is 0. Go over pi over 2, my y value is 0, and this gives me just the natural log of 2. So here's what I noticed as well. A good amount of students had this. They had all of this, and then they misinterpreted the question, right? Find the absolute max value. Find the absolute min value. So in their work, they said, ooh, all right, these two are absolute maxes because they're the same. And then they said absolute min. I'm not quite certain if the AP test is going to give you that as an answer. So here's what I'd ask you to do. You always relate it back to the original function. Okay, so f of x has an absolute max of, that's what they're looking for. What is the absolute max? It's the output. And then where does it occur? At x equals pi and x equals 2 pi. Okay? And if you really, yeah, that's probably good enough. And then we have to write the other one. F has an absolute min of, what is the lowest output we have? It's 0, or you could write ln of 1 at x equals 3 pi over 2. So notice what I did. I stated what the absolute max or min was, and then I stated where it occurred. If you do that, then you'll answer any question that they could ask. It's a little bit tricky, because there's a lot going on here, but it's a pretty quick problem. So let's take a look here. It tells us that let g be a continuous function where g of 2 equals 5. The graph of the piecewise linear function g prime is the derivative of g is shown from -3 to 7. So you always need to make a connection. What graph are you looking at? Here they tell us to find the average rate of change of g prime from -3 to 7. Well, all that's asking for is the slope. So if I found the average rate of change, that would be the slope of that blue dotted line, and that was the first thing they asked for. So I'm going to take the negative, actually I'm going to take 7 minus -3, that's my x values, right? Some people like to call it a and b, so it's the difference of b minus a over the difference of y values, so f of b minus f of a. And if you do that, you end up with 5/10, or 1/2. You got 1 point if you said the average rate of change is equal to 1/2. Right? And maybe we should be careful, the average rate of g of x, right? That's officially what we found. Now that's the first part. The second part of this question says, does the mean value theorem applied on the interval guarantee a c value such that the derivative is equal to the average rate of change? So is there a value that's equal to this 1/2? Well, first thing we have to look at is this graph continuous? And yes, it is continuous. So that checks off the first part of the hypothesis, but this graph is not differentiable at those points. So the only thing you need to say here is the mean value theorem cannot be applied because g prime of x is either non or not differentiable over the interval of -3 to 7. And there's different ways you can explain that, but that's it. You just have to say it's not differentiable. You don't have to say why. That you can say the slope on the left is not equal to the slope of the right at these 3 points, but just using that word non-differentiable, you're done. Okay, I hope that helped answer some questions, and I kind of treated this as a review as well. So we've got a couple things to talk about here quick. The test. So starting, as soon as we're done with class, you could technically start the test if you'd want. It's open and available. It's on Schoology, and it's 50 points summative. It's going to cover section 5.1, which is finding critical values and then determining if they're max or mins, and are they local or absolute. We did an example of absolute where you don't need a sign chart. You just plug them into the value, which one's the highest, which one's the lowest. If you're determining the local values, that's where you need the sign chart to see the change in the first derivative from positive to negative or negative to positive, and that'll determine maxes and mins. Section 5.2 is the mean value theorem. So remember the hypothesis: the function must be continuous on a closed interval and open on the differentiable on the open interval. And then you can compare the instantaneous rate of change to the average rate of change. That was also the section that was introducing the increasing and decreasing, but we actually talked about the increasing, decreasing functions when we did 5.1. So we kind of combined these two sections a little bit. And then we talked about concavity. We're going to review a problem like that today in class. And determining where a function is concave up or concave down, that's all the second derivative. And then remember, inflection points are where the second derivative is equal to 0 or it doesn't exist, and there has to be a sign change. So it has to change from concave up to concave down or vice versa. And then we talked a little bit about interpreting and sketching graphs. If I gave you a graph, you'd have to match it back to the original function. And we're going to review that. So test is on Schoology. You're going to have a combination of multiple choice, fill in the blank. There's some drag and drop style questions. There are actually 3 file upload problems, not 2. That means you're going to have to submit that image to Schoology for each question. And the reason why we do that is because you're going to have to do that on the AP test if we take it online. So we got to practice that. And you should really kind of try to really get down that, take a picture, submit it, and do that in the fastest amount of time you can so you're ready for it when you get the AP test. All right, and then make sure any images you take are clear, taken in a room with plenty of light, and those images are clearly visible before you submit them. And the test will be it's actually available right now. And you have until Sunday night at 9 p.m. to finish the test. The reason why it's not 11:59 is I don't want you staying up that late. You should get some good sleep before Monday, Tuesday. And then, as always, at the end of the test, we've got a separate assignment in Schoology where you're just going to submit all of your work. So when you're doing this, please number the problems, number 1, number 2, and so on, and show your work for every problem that needs it. Some of them are graphs where it's really quick, and obviously you won't need to show work for those. All right, I'd like you to send me a private chat right now based off of the information right here. So let's say that I gave you this information. F of x is differentiable for all values of x. F prime of x at 5 is equal to 0, and f double prime at 5 is equal to -6. What do you think you can conclude about the point at x equals 5? Send me a private something that looks pretty quick, right? Which this problem is quick, but there's a lot to decipher here. So f of x is differentiable. If it says that f of x is differentiable, that means the derivative exists. And I actually probably should have said it's twice differentiable because that means the second derivative exists as well. I should have probably thrown that in there. But if it says it's differentiable, it also implies that f is continuous. So we know our function is continuous and differentiable for all x values. That's just kind of a given condition for us to make a connection to the next 2 pieces. Then, people were right in the fact saying that at x equals 5, we have a critical point. Why? Because the derivative at 5 is equal to 0. Now, here's how I would approach this problem. We don't know exactly where this point is. We know that there does exist a point at 5. And we know that it's a critical point, which means the derivative at that spot has to be 0. Right? The slope is 0 at that small moment. But what other conclusions can we make? And that's where the second derivative comes in. Now, I really don't care about this number 6. What I care about is the fact that it's negative. Right? So what does this mean? F prime of 5 is less than 0. When the second derivative is less than 0, a couple of people noted this, it is concave down. Well, let's think about that. If the function has to have a 0 slope at 5, and for the rest of it, it's concave down, or at least at that moment, we don't really know that this graph looks this way, but this is kind of how I interpret it. If the graph is concave down and I have a flat spot, and this is a critical point, what kind of point is existing right there? It's a maximum. It's the highest point of all the points around it. Right? So that's our conclusion. And how would I justify this? I would say f of 5, notice it's the original function at 5, is a maximum. And then if they ask me to justify the reason why, is all you need to do is state that, basically restate the information. This is a critical point, and I would state this as x double prime of 5 is 0. So if you have a critical point and you know it's concave down, then the only point that can exist there is a maximum. And this was that second derivative test that we introduced. So we introduced this, I think it was Monday or Tuesday, but we really didn't do a lot with it. So I just wanted to throw another option out there. And notice, really think about each piece has a value to this point, and I'm a visual learner. So if I can connect to it graphically, it makes it a little easier for me to solve and think about. All right, now, how would this change if I changed this to a positive 6? Right? If this was a positive 6, we wouldn't be concave down, it would be concave up. And instead of looking at a max, it would be a min. So the second derivative can also help us identify where maxes and mins occur. And that's what the second derivative is all about. All right, I'm going to do a zoom poll on this one. So give me a second to set the zoom poll up, and then I'll have you respond to it. But for right now, I'd like you to just kind of read through this. Here's the problem. You're given the graph of f prime, which is the derivative of f. The domain of f is open from 0 to d. Which of the following statements is true? A through E. And I'll set up a Zoom poll that you guys can respond to. Okay, the poll should be available. And let's just see what you think. I always just like to view this because in my last hour, we had like a 33% breakdown for B, C, D, and we had one person guess E as well. So here it is. I'm not saying the answer is any one of these yet, but let's go through and look at it. 9 people out of our class said the answer was B, 5 said C, 6 D, and 1 said E. Nobody said A. So let's take a look at how we can approach this. And here's my advice. We have a graph that is the derivative, right? That's the first thing you need to connect with is this is the derivative, but everything else, everything was referring to the function f. So I can't just look at this graph and make a conclusion directly. I have to make a connection to how this relates back to the original function. So here's my advice. Let's make a sign chart of what we know. Where is the derivative equal to 0? That's A and C. Those are critical points. And then what are the signs of the derivative to the left of this? Well, they're below the x-axis. So when you're below the x-axis, that means this is the graph of the derivative. They're negative. So my signs are negative. And then when I'm above the x-axis, that's between A and C, the derivative is positive. So you can put that here if you'd like. And then when I'm below the x-axis again, I'm negative again. Well, look at this sign chart. This might help me answer a lot of these questions. F has a local minimum at C. Well, here's C, but I go from increasing to decreasing functions. So this would be a maximum of the original function f. So it's not A. F has a local maximum at B. B does have a derivative of 0, but what is that derivative? It's the second derivative that's 0, because it's the derivative of this graph. So we're going to make a connection to the second derivative in a second, but it's definitely not a maximum because I would have to have a change in the first derivative there for a maximum. The graph of f has a point of inflection at A. Ooh. Well, let's see. At A, we know for sure my slopes go from decreasing to increasing, so this is a minimum. All right, so right now, I have a minimum here, but let's look at the slope of this tangent line. The slope of this tangent line is not 0, and for critical points, or excuse me, inflection points, for inflection points to be an inflection point, the second derivative has to be 0. So the slope right here would have to be 0, so it is not C. And then it says the graph of f has a point of inflection at B. Well, B has a slope of 0, so the second derivative is 0. And actually what I might do is let's make a sign chart now for the second derivative. All right, so this is the graph of the second derivative. And remember, if I'm looking at the first derivative graph, the second derivative is the slopes of this graph. So where do I have a 0 slope? Right here at B. And then what do you know about the slopes to the left of B? They're all positive. What do you know about the slopes to the right of B? They're all negative. And this is a second derivative that goes from concave up to concave down, which means, yes, there is a point of inflection at B because the derivative is 0 and there's a sign change. So the correct answer is D. And then let's just confirm that E doesn't work. The graph of F is concave up on the interval from C to D. Well, look at, because the second derivative is positive here, positive slopes, that means we're concave up from 0 to B. So that does not work either. So notice, a sign chart can help you a lot. And if you have the graph of F prime, you can easily make the F prime graph or sign chart. And then you can look at the slopes of this line or this graph to make the graph of F double prime, which means I can determine concavity and increasing, decreasing, max and mins. I can basically determine everything. All right, so here's another one. And actually, I'm going to give you about 5 minutes on this to answer. Maybe we'll go a little longer. But let's read through this quick so you all understand it. And I'm going to give you a hint. Okay, the graph below is G prime. So that's the derivative graph. Use the graph to answer the following questions. If there's not enough information, just say cannot determine. So notice what we're looking for. Here we're going to ask a lot of different questions. Some of them are related to the graph that's given. So this is the G prime graph. Some of them are not. Some of them are related back to the original graph of G. And then even more, some are related to the second derivative. So really look at what's going on. And my hint to you to help answer these questions, see if you can make a sign chart for G prime, which is given, and then make one for G double prime. So I'll give you about, let's say, 7 minutes on this. We'll come back at 10 after 9. All right, so let's take a look. You may have not had a chance to go through all of it, but I pre-filled this out as we were, or as you were working, I filled it out too. So this is the graph of the derivative. Let's take, before I even look at any of the questions, let's take and just make a sign chart for this graph, exactly the way it looks. So what do we notice? When is G prime equal to 0? 1, 2, 3. 3 spots at -6, at -1, and at 6. So those are my critical points because that's when the derivative is equal to 0. And then I'm looking for when is this graph above the x-axis. It's above the x-axis from -7 to 6, so that's G prime is positive. It's below the x-axis between -6 and 1. It's back above the x-axis above the x-axis between -1 and 6, and then it continues to be above all the way to 10. So then I can make my sign chart. Now notice, this is the derivative. right? So now we know we're increasing, decreasing, increasing, increasing. We could determine, I go from positive to negative, so I have a max, here's a min, there's a flat spot. All of that can be determined just from this graph very quickly. And then let's look at the derivative of this graph. So if this is g prime, then I'm going to look at the derivatives of this graph, or the slope of this graph, to help me make conclusions for the second part. So now let's look at the graph of that. Well, where do I have zero slopes or horizontal tangents? We've got some horizontal tangents, there we go, at 3 spots, right? At -4, that's when the second derivative is equal to 0, at 2, and at 6. And then we're looking for the slopes of that leading up to it. What do you notice about the slopes here? All of these slopes are negative. From -7 to -4, g prime is decreasing. And then, what do I notice here? My slopes are positive between -4 and 2. And then my slopes are negative, and then positive again. So now I know where critical points are going to occur. I know when the original graph is concave down or concave up. All of that will then help me answer these questions fairly quickly now. So when is g prime equal to 0? Well, that's my critical points. So g prime is equal to 0 at these 3 spots, -6, -1, and 6. That's when g prime crosses the x-axis. 1, 2, 3. All right, so now on what intervals is g increasing? Notice this is the original function. So when is the original function? That is when oops, I should, instead of f, this should be g. That's when the original function is increasing when the first derivative, g prime, is greater than 0. So look at your first sign chart. When do I have positive slopes? From -7 to 6, from -1 all the way to 10. Now you could have also said -1 to 6, and then 6 to 10. I've seen this written 2 different ways. They'd accept either way. All right. At what values does the regular function g have a relative minimum? So we're looking at a sign chart. Here I go from increasing slopes to decreasing slopes. So I've got a max at -6. But then I go from decreasing to increasing, which is a min. And when there is no sign change, we're not positive. This could be a flat spot, but it's not a max or a min because there's no sign change. So at x equals -1, there's a relative min, and we know that because f prime changes sign from negative to positive. All right, and then at which prime does the second derivative equal 0? So which x values does the second derivative equal to 0? Well, this is the graph of the derivative. So if I take the derivative of it, those are where I have horizontal tangents on g prime, which we already have written out here. Those are my potential points of inflection. So -4, 2, and 6. And the reason why we know that is g prime has horizontal tangents. There are a couple of reasons for this next one. On what intervals is g concave down? Well, that's when the second derivative is negative. So if you make your sign chart, you can see kind of quickly where we're going to be negative. Notice I didn't put negative infinity because my interval ends at -7. So you do have to be aware it's -7 to -4, and then 2 to 6. That's when we have negative second derivatives. But what if I just wanted to look at the graph to get that information? What's another way we could justify this? Or we can say that the original graph has to be decreasing. Right? So when do I have negative slopes on G prime? From the same interval, negative slope here and a negative slope here. So you can say when G prime is decreasing. All right, last one. When does the original graph G have points of inflection? Well, that's true when the second derivative is 0, so when we have the horizontal tangents, plus it changes signs, and that's why I like using a sign chart. You can see the 3 spots where G prime is equal to 0, and you can see we change from concave down to concave up to concave down to concave up. So every single one of these has a sign change. All right, let's go over this quick. I just kind of did it here, and I'll just show you really quick. I didn't realize we have 2 minutes left. So if we're looking for concavity and points of inflection, that deals with the second derivative. So we're going to take the derivative of the first one, then the derivative of the second one, and then I factor out a 12x. Set each one equal to 0 and solve, and I get 2 possible points of inflection at 0 and 1. Make a sign chart for the second derivative at 0 and 1. Test the values to the left and right, get your sign chart, figure out. Now, I am testing this in the factored form of the second derivative because it's easier to do that. And then just test those values. We get positive, negative, positive. Concave up is when we have positive second derivatives. Concave down is when we have negative. And points of inflection occur if there's a sign change, which there are, so 0 and 1. Okay, that was really quick. Again, I'll post these notes. I want to just touch base really quick. We're not going to do this one. But basically, it was a mean value theorem that on this interval, it didn't work because it's non-differentiable. On a different interval, it did work. So the same function can work. It just depends on what part of the interval it works. Okay, so the test is available now. You have until Sunday at 9 p.m. to take it. Make sure you show your work for all of the problems and you submit that to Schoology when you're all done. And then the last thing, if you would like to do some extra practice, this is optional. These answers for both the AP review and the review exercises are in Schoology already. They're already posted there, so you can go ahead and check. And maybe look through it and do 1 or 2 or do them all. And you can do this before you take the test. So that's all I got. I will be available from 1 to 2 in my office hours today if you have any questions. Otherwise, have a great day.